50 dx. So to make a long story short, the di with the right mumbo jumbo units is going to be 50 dx. It's going to be 50 amps per width meter times a differential amount of meter. Is how it comes out. Okay? Where did the 50 come from? It came from doing a ratio. This is the better way to do it, actually. This is the better way to do it. They make dx, let's say, basically, if you say x equals r, dx is going to be dr. Now, what's that? See what you got. I would take it from here all the way to here. That's r. From here all the way to there. That's another r. Here are the r's. Go right to the middle of the wire. The wire is so thin it doesn't really matter. You can make them thin strips of wire. And that's how you're going to do it. And the dr is just you go over to another place. So that's really this is really the ticket, you guys. This is really the better way to write it. If push came to shove. I mean, probably the very best way to write it. You know, there's so many ways, so many looks at this. This would work, or you could even say, let's go here right off the bat. The whole length of the thing, the whole width of the thing, times every differential portion of it. In other words, it's going to be always 4 times the differential length, the differential width compared to the entire width. Yeah, well, 0.08 goes into 4. 0.08 goes into 4 50 times, 50 dx. And then I just said x and r are the same, so it's going to be 50 dr. So that's where you want to go. This is to me, this is the best, and you don't even have to deal with the pseudo j. You know, the j has been, to my knowledge, has been defined. The j has been defined somewhat differently than how I use it here. It still works if you just kind of ignore a lot of formalities. It still certainly works. But I tell you, probably the easiest is right there. This is also good. This will work. This will also work. Certainly, they're born of the same situation, you guys. The whole thing comes right back down to here for you to make it look like that. That's better, though. That's actually better. Didn't quite do it like that in my notes, so I'm showing you right now. Very similar to that I did, but not quite. All right, this is important. It is a differential element of I. It's not a differential element of I going this way. Like, oh, a little I, a little I, a little I, a little I. No. It's all, the I's are all 4 amps. The differential element of I is split right here. It's, I don't know, whatever. It's 1,000th. It's only 1,000th the width of this guy. What does that mean? It's 1,000th what that is then. It's 1,000th of 4, which is 4 milliamps. And there's 1,000 of those 4 milliamps that give you the 4 amps, etc., etc. All right, so looking at this, I think that takes us to where we want to go. Let's do this with the R. Now the R is this, guys. This is the R. This is the R, and then right here is the dr. All right, let's see what we got. So moving along those lines, you guys, let's kind of take that. This is the way it kind of looks, the general structure of it, guys, as we've said. Okay, so let's do it. I mean, you're looking at this, we're figuring out where we're going to go. We got df is equal to mu0 Now, be careful. This guy is 2 amps, this guy is 4 amps, sort of, but we don't know what's going on here. There's a lot of differential stuff going on. For me to kind of tinker with it, this guy, yeah, I get it's 4 amps. Yeah, if it was one wire, it'd be 4 amps. But it's 4 amps spread out over an infinite number of tiny wires. So, I got to account for each one of those little wires because they're located in a different place from one another. Which means that the force on each individual wire is different because each one's further away from the other. Some are close, some are far away. Each one of these guys, there's a force here, there's a force there, a force here, there's a force down here. I get it, a force here too. They're all different. There's the beauty of calculus. Well, mu zero, the 2 amp guy ain't an issue. The 2 amp guy is not an issue. The L is this guy. This guy's going to be the DI. Let's just write it a little bit differently. Sorry about that. LDI. The way I wrote it's the right order, but so it's a little way easier if the differential is way at the end, I guess. Let's go. Integrate. What are you talking about? I'm talking about taking a walk. This right here is 4 centimeters from here to here. That's 0.04 meters. All the way to here is 12 centimeters. I know this is 8, but 4 and 8. Remember, we're starting here. We're starting here. 4 and 8 is 12 centimeters. Here's 4 centimeters. 0.04, 0.08, add them together, that's 0.12 meters. So you start at 0.04. .18. Here we go. The 2 they gave to us. 2 is this guy. Remember now, emphasize this. 2 is this guy. The 4 is everybody. So I got to break them up. And this is the breakup. This guy does the breakup for us. All right, well, that 50 DR I wrote earlier, over 2 pi r. Sounds good to me. I tell you what, we kind of got to be careful here. Now, let's see where this is going to go. For some reason now, I want to just make sure we've got this straight. We've got the L. Okay, let's talk. The L does not vary. The L was this guy. The L does not vary. It's got a length associated with it, but it doesn't really vary. Why? Because I arbitrarily said, hey man, this thing goes on forever. I'm going to make L 10 meters long. This is a 10 meter long sheet that happens to be 0.04 meters, that happens to be 0.08 meters in width. 0.008 meters in length, 0.08 meters in width, and L meters in length, 0.08 meters in width. The L is constant, you guys. If the L is constant, do you mind if I divide by L on each side? F over L is the force per unit length. Equals the integral. Here goes. I mean, dr varies. Everything else a constant. So there's probably a lot I can throw out. I can get out of there. Get out. Let's see what we got. Divide by L on each side. The L's gone. 2 times 50 is 100. 100 times mu 0 divided by 2 is 50 times mu 0 divided by pi. So let's see. Forgive all the stuff here, guys. It's all over the place. 2 goes into 2 goes into 2. 2 goes into 2 once. That's it. We got 50 we've already divided by L on each side, did this division. We got 50 mu 0 over pi. Mu 0 over pi, divided by L on each side, so the L's out of there. We got dr over r here, the integral from 0.04 to 0.12. All right, it's quite about, you know, whatever, it's a long song and dance, but it's not too bad. We look at it, definitely going to get more chalk. So what do we got? You've got 50 mu 0 over pi. The integral of this is ln r. Evaluate between 0.04 and 0.12. That's ln. And we'll multiply it below that. That's ln 0.12 minus ln 0.04. The difference of two logarithms is the logarithm of the ratio. The difference of two logarithms is the logarithm of the ratio. Well, that's pretty simple. Comes out to here. Comes out to there. So that's what you put right here. You're done. You've got, you know, at the end of all that, you know, when you're looking at what just happened there, you're saying, what is the force? It's very interesting. You had to have an L here. You can't just not have an L here, because they want the force per unit. They want the force per unit length. So you got to have a length associated with it. But I don't need to really talk about a J in this case, guys. I need to talk about a differential amount of current associated with an area that's a differential amount of area. And that's really the takeaway on that. The ratio of widths, if I take 1/3 the width, if I take a sheet out of there, that's 1/3 the width of that sheet. That 1/3 width of sheet has 1/3 the current that was in the big sheet. It's 1/3 of the 4 amps for the whole thing. If I take 1/3 a 1/3 sheet, it's going to be 1/3 of that 4. It's going to be 4/3 amps. If I take 1/4, if I take 1/4 of a sheet, 1/4 of that width, that'll tell me it's 1 amp for every one of those quarters. All right. Making the long story short, I guess you could say, we got this. We got at the end of the day, and they got, you know, you can put the actual numbers there and stuff and everything. Like I said, myself, I'm a little partial to the way you can actually write this thing. You can write it like this: 50. Let me see here. You know, 50, and then this whole thing would be 50 mu 0 pi ln 50 mu 0 pi ln 3. You know, that's pretty. It's a rather, to me, this is. I mean, depending on how the question gets asked, I guess, you know, but that's pretty aesthetically, looks good aesthetically. This mu 0 means 4 pi times 10 to the negative. So you'd also have this as we go through here. The mu 0, you know, the mu 0 is 4 pi. Over pi times ln of 3. So you got this. There's a lot here. I mean, obviously, but the way you're going to make it happen, that's out of there. It's going to be, F is going to be 200 times 10 to the negative 7. Just watch what you're doing, guys. I mean, at the end of the day, you know, where is this going to go? When this thing, when you're done with this whole thing, that thing's going to grind out, and you can write it a whole bunch of ways here. The way I have it in the notes at the end of the day is 2.1972 times 10 to the negative fifth. 2.1972 times 10 to the negative fifth newtons per meter of length. The real big move is getting to here, doing this. Once you get to here, the rest is academic, as they say. That is all of what I wanted to say related to chapter 30. Thank you guys. Good luck to you.